Okay, great. Next, we want to do a log-log model. So we're going to do the natural log of soda expenditures as a function of the natural log of income. Again, I would go back to the lecture material. When we have this log-log model, this beta 1 here is going to tell us the percent change in soda expenditures given a percent change in income, which is by definition an elasticity. So log-log models, the coefficients on log-log models are direct estimations of elasticities, which is really cool. So we're going to run this model. What we need to do is create two new variables. We need to create the natural log of soda expenditures and the natural log of income. So we're going to go back to our Excel document, back to our original data. What we have is spending and income, but we need the log of both of those things. So I'm going to, again, I'm just going to insert a couple of columns on the Home tab. Go over here to Insert, and click that a couple times. So first I'm going to create the log of spending, say the natural log of spend. Okay, and that's going to be equal to ln of the soda expenditures for a given individual. Okay. Pause here, make sure you have the right formula. Okay. Hit enter. And then we want to copy that same formula for the rest of the observations. And there we go. We have the natural log of soda expenditures. Let me turn my email off there. Great. Okay, and then the next variable we need to create is the natural log of income. I'll call it ln income. And that's going to be equal to the natural log of income for any individual. Pause here to make sure you have the right formula. Okay. And then we want to copy that for the rest of the column. And there we go. We have natural log of soda expenditures and the natural log of income. We can run our model. So we'll go to data, data analysis, regression. Our Y range here is going to be now the natural log of soda expenditures. Our X range is going to be the natural log of income. Include labels, and now we're going to send this to a new worksheet. I'm going to call it a log model. Hit enter. And there we go. We have our regression output table. And again, if this is going too fast for you to follow along as I do it, no worries. You can pause this at any time and catch up. Okay. So the adjusted R squared, not great. We're gonna fly through this. Not great, right? The F stat here is greater than 0.05, so we're going to actually fail to reject the null, meaning that the natural log of income, our only slope parameter, is not significant. So this model is not jointly significant, so it's not a good model. Okay, and sure enough, if we look at the p-value on this coefficient, it's 0.19. Again, greater than 0.05, meaning that this coefficient is insignificant. Okay, not a great model. That happens a lot, but just for the sake of this example, we're going to pretend that this p-value is, let's just pretend out here that it's 0.0003, okay, which would make this a significant result. So I'm just going to copy these here. So let's just pretend for a moment that this is a significant result if the p-value is, for example, 0.0003. What this means is that as income increases by 1%, soda expenditure should increase by 0.26%. Okay, it might be attractive to think that a 1% change in income will result in a 26% increase in soda expenditures, but that's incorrect. With a log-log model, this number here is the percent change directly. Again, go back to the lecture material, and there's a table there that explains that exactly. So again, a 1% change in income results in a 0.26% change in soda expenditures. Okay, it's positive, meaning that this is essentially a normal good. As you earn more, you're going to spend more on soda expenditures. All right. Cool. So that's our log-log model. The last model we're going to do here is not from this data. It's actually, for your benefit, it's from problem set 5. So this is, we're going to model corn yield as a function of water inputs. This is a quadratic model. So it's a function of water plus water squared. And this here is going to give us that U-shaped curve. So if you go to Excel, pull up the problem set 5 Excel document. So this is actually one of the questions on the problem set. So if you're watching this before you complete the problem set, congratulations. This is going to give you an answer. Okay. So here we have information on corn across many states in 2019, area harvested, area planted, total yield in bushels per acre, and then water in thousands of acre feet. Okay, and then we go back to our model. We want to model yield as a function of water and water squared. So we're going to have to create this water squared variable. So I'm in column I here. I'm just going to say water SQ, water squared. And that's going to be equal to water to the power of 2. I'll pause here, make sure you have the right answer, the right formula. Okay, and we want to copy that for the rest of the observations. And we're ready to run the regression. So we go to data, data analysis, regression. Our Y range here is going to be total yield in bushels per acre. Our X range here is going to be water and water squared. Include labels, and we're going to send this to a new worksheet, call it quadratic. Okay. Hit OK. And there we go. There's the regression output. So the R squared here is incredible, right? 0.99. That means that water and water squared is explaining 99.9999% of the variation in yield. That's suspiciously good. It's suspiciously good because I had to create this data. So I made it good. Okay, so great, adjusted R squared. The F stat here is very small, meaning the model is jointly significant, meaning that at least one of these variables is significant. And if we, one of these coefficients. And if we look at the p-value on the coefficient associated with the intercept, water, and water squared are all highly significant. So how do we interpret this? So this gives us this U-shaped curve, right? So we can predict the amount of yield given the amount of water usage. So remember our formula here is, I'll just type it again here, yield is a function of this beta naught plus beta 1 times water plus beta 2 times water squared, right? So now we've estimated that model, so we can directly estimate the yield given any amount of water. So we can build a formula real quick. I'm going to say yield is going to be in this cell B24, and then the water use is going to be here. Okay. So the yield is going to be equal to beta naught, which is this intercept here, plus beta 1 times water. So it's this coefficient beta 1 times water, and I'm just going to use an input cell here, so I'll just reference this water cell, plus beta 2 multiplied by, again, that water cell squared. All right, so we've just recreated our model, but now we're using the actual coefficient estimates from our regression. Okay, hit enter. Right now water is 0, so it's predicting if we're not using any water, our yield is negative, which doesn't make much sense. So if we go back to the corn production just really quickly, water usage in 1,000 acre feet ranges from pretty low all the way up to around almost 200. So let's say our water usage is 50 acre feet, then we can predict a yield, or we do predict a yield of 172 acres per bushel. if the water is 51 feet, our yield increases by a little bit, about 52, again increases, and eventually if it goes up to 100, it's going to be a lot bigger. But if we use 300 acre-feet of water, again our yield's going to be back to a negative because there's this U-shaped curve. Okay, so if we want to solve for the maximum amount of water usage, then, or the optimal amount, then we're going to try and optimize yield as a function of our water inputs. It's just like any other unconstrained optimization problem. We're going to need to take the partial derivative of yield with respect to water. So the partial effect of yield with respect to water is just beta 1 plus 2 times beta 2 times water. And we set that equal to 0, like any optimization problem. And if we do our algebra right, we're going to see that water optimal, this optimal amount of water, is going to be equal to negative beta 1 divided by 2 times beta 2. Okay. We can actually just solve that directly. So our optimal water is going to be equal to negative beta 1 divided by 2 times beta 2. Make sure you have that formula right. Hit enter. And there we go. According to this data, the optimal amount of water usage is 117.5 acre-feet of water. Okay. So if we go back to our prediction of yield, if we say 117.5, our yield's going to be 263. That's the maximum yield that we'll be able to reach. If we go up to 118, our yield is going to drop by just a little bit. If we go down to 116, our yield is also going to be less than if it were at 117.5 or 117.499977, for example. Okay. Cool. So that's an application of estimating a quadratic model and then using the results to predict yield and also find the optimal amount of water to maximize yield. All right. And there we go. That concludes the second review video.